Okay, that's f of theta. How would you pinpoint location on the graph? Furthest to the left or furthest to the right? So think about that. So how could we figure out? And then that could be just locally too. Like, so how do I pinpoint the point way out the furthest to the left? Oh, there's another one here that's kind of locally furthest to the left, right? And then here and here, or furthest to the right. Sorry. This would be furthest to the right, here and here. What about furthest up or down? Okay. What about how would you find points that are furthest from the pole? Right. Locally, they kind of have a maximum value furthest from the pole. And then how would you determine dy dx for a given point on the graph? So we haven't talked about that with polar functions yet, but we have seen a similar idea before. So take a couple minutes, talk through these questions. We don't have time to do examples of all this because we got to get onto area. But in terms of getting your web work done, these will be critical ideas for solving the problems. Take a couple minutes to talk about those. Go. Okay, so how am I going to pinpoint these places that are furthest to the left or furthest to the right? What do we think about that? Samantha, what do you think? Dy equals 0. So as we're going through here, changes in y where there's 0. Agree with that? Some are nodding in agreement. Some are suggesting dx. What doesn't change through here? What doesn't change at that point? X or y? Now people are saying x. You agree? Yeah, it's going to be dx. So what do we want to set equal to 0 then? Dx? How are you going to get dx? Where's dx going to come from? What's that? So we have r as a function of theta, right? We have r as a function of theta. What do we want to set equal to 0? Dx? What's that? Yeah, dx d theta, right? So we're going to take a derivative with respect to theta, right? Everything's in terms of theta. And remember, what does x equal? That comes from x equaling what? R cosine theta, right? And what's r? F of theta on this graph, right? All the r values are f of theta. So that's why when you do that x dx d theta, it'll be the product rule, right? Product rule, f of theta times cosine theta is what you're taking the derivative of. Okay, I want furthest up or down now. Like locally high points or low points. So same thing, but now dy d theta. And then we did an example like that last time, I think, right? Okay, furthest from the pole. So we might guess here this is pi over 4 and 3 pi over 4, but if we couldn't make that guess and we wanted to be sure we were right, how could I get these points furthest from the pole? Need to hit those. What do we think about that? Riddick, yeah. He wants dr d theta equals 0. Agree? So what furthest from the pole are we? We're asking, does r not change for a moment there, right there? Does r not change for a moment? Yeah, because for a moment there, you're not going away or towards the pole. You're going somewhat like parallel to the pole for that moment right there. So yeah, dr d theta equals 0. How would we get dy dx? So I say I want to write the equation of the tangent line at 2 pi over 3, which is right here. I want to write the equation of that line. And so what do I need for that? I need dy dx, or the rate of change of y with respect to x. How am I going to get that? If I want to write the equation of that tangent line right there. Anna, what do you think? Everything's in terms of theta. All the information we have is in terms of theta. Yeah, so we saw this before with parametric functions. That's right. So each of those is a product rule, and you're going to again, but then this will be what? This will be some function of theta. So it's different. So it's the same rate of change that you've been used to all through Calc 1, but now it's not a function of x, it's a function of theta. So to get that point, you'll have to plug theta in. You plug your 2 pi over 3 in, get your point in terms of x and y, and then plug your 2 pi over 3 in, and you get your rate of change, and then you just have a equation of the tangent line. You've done a million of those, right? All through calculus and before. Okay, so that's kind of an overview without doing a whole long example. I think you've got all the tools to solve those problems now. The current web work is due Monday, I think at 5, and then the stuff that we finished up with today, there'll be another web work. So there'll be 2 more web works. The one that's currently posted and 1 more on area. Any questions on these questions or how you would approach this? Okay, so we want to talk about accumulation of area with polar coordinates, our last topic. So let's go back and review what we talked about with accumulation of area for standard y and x coordinates. We started with this. And we said, if we want to derive an accumulation function, what do? We look at the constant rate of change situation first. Remember that? We always looked at the constant rate of change situation first. So here's the area changing at a constant rate. And at what constant rate is this area increasing at? What constant rate of change is this area increasing at with respect to the horizontal coordinate, the width? Oh, please knows this. It's the constant rate of change of area. Which is what? 5, right? So the area d, so it's like dA dx. dA dx, in this case, equals to? In this case, equals to 5. And we could do that by saying, okay, what's the area, say, at, I don't know, what is this? Say 8. So when the area is 8, what was the, change in x? When our change in x is 8, what was our change in area? 40. And so then, because it's a constant rate, all we need is 1 dA and 1 dx, and knowing that we're at a constant rate, then we can know what the rate is exactly, right? Then we say dA dx is 5. And then we said, oh, look, it's just the height of that thing, right? It's just the function value. Okay? So then we took that knowledge, and we said, well, what about if the function is changing, right? Remember this? So we're going to do all this same stuff with polar. Here we go. This isn't the one I wanted. It's the next one. No, this is not the one I wanted. Is it this one? This is the one I wanted. Remember this? We said, okay, well, what's the rate of change of area when the function value is constantly changing? So what did we do? We said, well, let's zoom in at any particular x value and consider little tiny constant rates, right? Little tiny constant rates. And now we can apply that principle that we just talked about. At a constant rate, what's the rate of change of area? So across these constant rates, the rate of change of area is the function value. So we can just make these little intervals really small, and these constant rates or these constant function values will mimic that function really well. And then we know that the rate of change is the value of the function, right? That for area, right? For area, the rate of change was value of the function. So we're going to apply the same thing to this whole same conversation to polar coordinates. So let's take a look. So the first thing I want us to do is, one more practice. Let's just do from 0 to pi. Try these two. Cosine theta plus 1, 5 cosine theta minus 2. No technology, no calculators. Can you sketch the polar graphs? And let's just go 0 to pi for time's sake. Cosine theta plus 1, 5 cosine theta minus 2. See if you can sketch both these in a couple minutes. If you've got your polar graph paper, that's really helpful. Okay. So I'm going to graph them at the same time. Ready? See how you did. See how you did. Ready? Here we go. So 5 cosine theta minus 2 should start at 5 and start decreasing. Cosine theta plus 1 starts at 2 and decreases. Yeah, so far? And they decrease, but they're going to decrease differently, right? Somewhere they intersect. We're going to find that in a second. So which one's decreasing faster, F or G? For which one are R values decreasing faster? Should see F, right? It's started at 5 and it's less than, the R value is less than G, which started at 2. Sorry, is that 3? I'm saying that's 3, not 5. Sorry, that's 3. Okay? And then somewhere before pi over 2, 5 cosine theta minus 2 hits 0. Goes through the pole. And then is in negative territory, whereas cosine theta plus 1 at pi over 2 has decreased to 1. So how'd you do from 0 to pi over 2? That's what these graphs look like. Well, we just care about that much right now. Did you get most of it or all of it? Some nods. Good. Okay, cool. Any questions on graphing those? No technology. It's on the final. Okay, so I pointed out that there's this intersection point. I want to pinpoint that place right there. So how would I pinpoint what's going on there that I might be able to pinpoint that angle and R value where those two graphs intersect? What could we do? Set what? So you set them. So what do you want to set equal to each other? What quantity? What variable? What's that? Y? Maybe, but it's not very convenient because everything we're doing is R and theta, right? So is there R's equal? Are the R's equal there? Yeah, the R's are equal. So how would we set r is equal? What would we do? R1 equals R2? Not very helpful. Is that setting, if I set g equal theta to f of theta, is that setting the r is equal? Is that setting the r is equal if I set the functions equal? If I say cosine theta plus 1 equals 5 cosine theta minus 2, does that set the r is equal? That's setting the theta equal or the r is equal? Andrew, what do you think? Yeah, the dependent variable of these functions is r. R is a function of theta. So r is cosine theta plus 1. That's how we got these points. And f is, or r is, 5 cosine theta minus 2. So this is the r from the first function, the g function, and this is r for the f function. This is setting the r is equal. All right, and so then we're going to solve and find the theta that makes this true. So quickly, 4 cosine theta equals 3. Cosine theta equals 3/4. So theta is r cosine 3/4. That's that light gray line that I'm showing you is the angle cosine, inverse cosine of 3/4 is that angle. Okay, and so then what is the r value? What's the cosine of the inverse cosine of 3/4? The cosine of the inverse cosine? Just 3/4, right? So the r value is 1 3/4. So we got 1 3/4. What is that? 7/4, comma, cosine inverse of 3/4 at that point. Now I want to know what angle here f of theta goes through the pole. How can I find what angle f of theta goes through the pole? So that's this angle right here. Something less than pi over 2, f of theta heads through the pole. How will I do that? Maya, what do you think? What's true about this point right here where this f of theta goes through the pole? What's true there? R equals 0. So how can I find that angle then? That's right, r equals 0. So to get that angle, what will I do? Yeah, so I'm going to set 5 cosine theta, that minus 2 is r, right? That's what that function does. It gives me r's for different thetas. I want to force that r to be 0. So now theta is going to be cosine inverse of 2/5. So that's that angle. And r is 0. Questions on that? Yeah?
So the 7/4 came from plugging the theta into the g of theta?
Either one. It's the same r for both, right? So I could do either one. I could plug it in here. I should get 7/4 too, because that was the whole point, that the r's are the same. Yep. Other questions? All right. Yeah.
What if there's more than one intersection point? What would that look like when you're solving?
Okay, good. So if there's more than one intersection point, when you're solving this, you'll have multiple solutions, and you'll have multiple solutions, and maybe that is the case. Yeah, so exactly, because cosine, so we knew we were in the first quadrant, so we could just do that. But cosine theta at 3/4 has what? Has other angles also. There's another angle in the fourth quadrant where cosine theta is 3/4. So we'd expect another intersection down here. So yeah. So yeah, this actually has more than one, that actually has infinitely many solutions theta. I just picked the one because we're in the first quadrant. Yeah, good question. Other questions? Okay, so let's talk about area. So what did we say? If we want to talk about area, accumulation of area with polar coordinates, it's going to be the same process we've used before when we did accumulation functions. So what are we going to think about first? What are we going to think about first? Just like we reviewed. What would come first if we wanted to build up to accumulation of area with polar functions? What's that? What kind of rate of change? What's that? Constant rate of change, right? So, what kind of graph in polar coordinates would sweep out area? So now we're talking about what? Area between the curve and the pole. So sweeping out area between the curve and the pole, accumulating area at a constant rate. What kind of graph would sweep out area between the curve and the pole at a constant rate as theta changed? Any ideas? Yeah, so a circle, right? Constant R. So we want a circle like, say, R equals, doesn't matter, do R equals 1.5. Do it in black. So can you imagine, as theta increases, area will accumulate between the curve and the pole at a constant rate because R is constant. So then how do we find that constant rate? What do we want? We want dA d theta. It's the same thing we did when we looked at the constant rate situation before. How do we figure out what dA d theta will? How much area is being swept out per change in theta? What do we do? What's that? Okay, but how did we build that up? How did we get there, right? It's actually, with circles, it won't just be the function value. So it's how did we build that? What did we do, remember? The rectangle? How did we figure out that dA dx was the function value? Yeah. Right. So I came over here and I said, oh, look at what happens when dx is 8. It was like a big chunk, right? It wasn't a little chunk. It was like the whole thing. And what did we say? So when dx was 8, dA was 40. And we got 5 for the rate of change. Same thing. So we need a theta and a corresponding dA that we know them both. Right? As theta changes, what could we do? Pick one that you know. Pick one that's easy. What's that? Which one's 2 pi? dA or d theta? Yeah, so go all the way around. Go all the way around. Change of theta 2 pi. And what is the area that gets swept out when you make it all the way around? Pi r squared. This making sense? So for that, the theta going all the way around, the area that we get is pi r squared, and so this will give us d theta. What is it? R squared over 2, 1/2 r squared. It's not the function value because now our independent variable is theta. That's not a distance quantity. That's an angle measure quantity. That's different. That's a different ballgame. So you don't just get r, the function value, to be the rate of change of area. You get this, 1/2 r squared. When you take this big chunk of area for a whole circle divided by the theta that you go through 2 pi. Okay, go away. Now let's notice something about this. This is going to be signed area. Remember we had signed area. When function values were negative, we had a negative contribution to this thing we called signed area. What about here? Is that going to happen? Is that what we're going to have? We're going to add whenever r is positive, we're going to add and then subtract whenever r is negative? Is that what's going to happen?
No.
Why not? What can you say about that rate of change? Always positive, no matter whether r is negative or positive. So what are we going to get? Always an increasing area, right? Whether it's r is in negative territory or positive territory, the area is just going to go up and up and up and up. That means when we have loops, what's going to happen when we have loops? We're going to like have redundancy, right? We're going to add things more than once. So maybe we might see that at the end of class. But just know this is not signed area. This is like an area function, but it's going to be kind of weird because we might get overlap. We might count accumulation of area that we've already counted before. Okay, so I want you to write. We're having fun now, right? Okay, last day. So let's see if this works. So I want you to write this accumulation of area function right here. I'm making it pretty today. Okay? So this accumulation, I want you to write this accumulation of area function using what you've learned this semester and what we just learned. Go. I want accumulation. And what's our independent variable going to be? Independent variable? Theta, right? Theta. These functions have an independent variable of theta. So I want this area accumulation function as a function of theta. Go. See if you can put it all together. Success. This is kind of like a final exam, kind of. Somewhat of a final exam question because it's such a key principle that we worked on so hard all semester long. How can I write the net accumulation function for area of G? Nick knows. Who else knows? Only Nick? Just raise your hand if you think you did it right. Not enough. Nick, tell us.
A sub G of theta equals integral from 0 to theta of 1 half.
Integral from 0 to theta of
1 half
1 half
cosine of t plus 1 squared
cosine of t plus 1 quantity squared.
dt.
The rest of you who raised your hands, is this what you did? Thumbs up. Nick made me proud. Thumbs down. But does it at least ring a bell?
Yeah.
Net accumulation function. All you need is the rate of change, and you can write it down. If you know the rate of change. What do we found out the rate of change for these accumulation of area for polar is 1 half r squared. So 0 to theta, 1 half r squared dt. That's going to be that function. Will for any given value of theta, will tell you how much area you've accumulated.
I thought that was just for a circle, that rate of change. Is that for every?
Oh yeah, so then we didn't really make the transition. But remember we said, no, it's the same thing as before. It's the same thing as before, right? So for this function we can take little thetas and consider that r value as a little circular arc. Right? Just like we did little changes in x and made little constant steps to match the function. Same thing. So for every little theta, we can pretend it's a little circular arc with a constant r for all these little changes in theta. And then it's the same thing. So it's the same as 1 half r theta squared. So just like we said, it's the function value when it's a constant rate, then when the function value changed, it was still the function value, was the rate. Same thing here. So when r is constant, that's the rate of change, but then as r changes, we can just make things small and consider little constant r values. And we get the rate of change as 1 half r theta squared. So yeah, if that messed you up, then you're slightly off the hook. But any questions? All right, so what about this? So now I want to do this one. Make sure I get the right one. Now I want to write this accumulation function. You ready? Watch. This. Wrong. Oh, it's here. Let me get this right up. So I want to accumulate to there, and then starting from there. Watch it again. Here's the accumulation function I want now. Accumulate area like this. When I get to my intersection, keep accumulating like that. Can we write that accumulation function? That's harder, but we did do it. We did do stuff like that. Work on it. See if you can do it. Take a couple minutes. Again, I'll show it again, see if I can do a better job here. Here we go. I'm going to accumulate area like this, up to there. And then like that. I want that area accumulation function. See if you remember that. But I want that as a function of theta, right? So this is from what? It will be for theta is from 0 to arc cosine is 2/5. I want to know what the area is for any theta in between 0 and arc cosine of 2/5. Okay, how do we do this? How are we going to do this? What's the general gist of this when we set up this function? What's the general structure to do this? Remember? The sum of two integrals? Is that what it is? Not quite. What's the structure of this function? What's the key word here? Piecewise, right? Piecewise. Did you write a piecewise function or attempt a piecewise function? Okay, good if you did. Let's see it. So now we'll call this one A2. So it's a piecewise function. So meaning that theta is going to take on ranges. What's the first range of theta that we were interested in? 0 to cosine inverse of 3/4. And so what will the function be for that? Right, it's the one we wrote before, AG. So I'm sorry, A2 of theta. Let's be a little bit more precise here. Okay, what about the second part? So now I want the accumulation of area all the way through the red and the blue. So it's the accumulation of area now after. So what's the new range of angles here? Theta goes from 2. Okay. And in that range of angles, what's my total accumulation or net accumulation of area? So the integral? Integral from? Starting from that starting angle to what? Theta of of what? 1/2. I'm going to use f. Is that okay? Because I don't have room. But I could, yes, you could write that out right there. Squared. Is that it? Is that a net accumulation of area function? Not quite. Not quite.
Well, so you would have to add a sub g of theta and change theta in the integral to.
Okay, yeah, sorry. I gotta need to do t's first. So that's not it. So yes, I need t's in here. That's one problem. Okay, good. But there's something else. Does this get the net accumulation in that second part? Is it the net accumulation of area since 0? Yeah, Daniel. Right, it's what? This is like total accumulation, right? It's all the accumulation from before plus the new change, right? That was an important concept we saw. So what is all the accumulation from before? So I could do what? A2, this function, at what? This needs to be parentheses. So I could recall the function by going back to the first line. A2 of what? Right? I need all that red area from before. If I'm going to keep accumulating, I need all that red area from before, which is what I get when I plug the final value of theta into this function, right? Or I could say AG. I could put AG here too. Would have been fine. Either one. That gives me all the red area from before, starting at arc cosine of 3/4, now plus the accumulating blue region, which is this here. Do I have it right now? Does that make sense? My last question was going to be, I'll just pose it and we'll say, I want to accumulate this area now. That's actually a little easier. So you can think about that. We can talk about it on the study session if you want. You can email me. Accumulate this area here, the purple area. What's the accumulation function for the purple area? Have a great weekend. Check Blackboard for all the announcements.
Would it just be the total accumulation of the blue function minus A2 of theta?
Yeah, so how could you write that all as one integral? So you're saying integral minus integral? Yeah, but so if we wanted to write that as one function, one integral function, how would we do it? So we'll call this A3. I want to do it as one integral. So what would I do?
Function minus the red function squared.
So the question is, there's kind of two ways. Is it 1/2? What is this, F? F. Is it that, or is it this? So would it be that or that? So that's the question. It's just not both. It's just one or the other. It's either this top one or this bottom one, which are different.
Bottom.
What's that?
Bottom.
They're voting for bottom. What do you guys think? Bottom?
Because you have to do both of them separately?
Yeah. So what will happen here is if you do f of t minus gt, and then you get a new single radius, like you're going to have some radius in here,
Yeah.
like some difference radius, and then you're finding from 0 to that radius, which will be a different area.
Yeah.
So yeah, it's this.
Why didn't we have to subtract on the second part of the first piece?
What's that?
Why didn't we have to?
And this one up here?